Okay, so welcome back to the class. So how do you feel with the homework? I see most of people can show the homework very quickly, right? Okay, so let's go to, so today class is very interesting. So after you learn very basic thing about how to do reachability analysis for feedforward neural network and how to do verification for it, and you can write your own code step by step, even it's not optimized, but you have general idea how things work. Okay, so today we're gonna discuss some very interesting idea in implementation and memory consumptions for verification algorithm. So let's remind what we have learned so far. We learn about feedforward neural network and how it's work, and the reachability analysis, and neural network verification. And then we learn how we perform reachability analysis using polyhedron. So we have two core steps. The first is phi mapping, and the second is the ReLU operations. And to do our ReLU operations, we have two options to do that. The first is using decomposition technique. So basically, you're gonna decompose a polyhedron into 2 power n sub polyhedron, and then you perform the ReLU activation function on each sub polyhedron, right? And the other options is the step ReLU operations. So basically, you're gonna transform a ReLU operation into a sequence of step ReLU operations, and then you can compute step by step, and then you construct a final reachable set after a ReLU operation. So this is what we tell about reachability. I got most of people know what's going on already. So we have a network, and then we have a set. We want to compute the output set of the network. Okay, so that's the reachability problem. And then to do that, we have layer by layer computations, which is I call a breadth-first-search computation. So and then we have two. So the computation reduced to the problem of compute reachable set for a single layer. So I see many questions from the homework that you cannot use the ReLU reach layer reach function for from the layer 2 or layer 3 in your homework. The reason is that you forget that after the first layer you have so many polyhedron, right? You have many polyhedron, and then you need to call that function in a for loop to compute the reachable set for the next layer. So in the class we discussed how we compute the reachable set for single layers, and then we combine all layers together to compute the reachable set for feedforward neural network, which have many layers. So keep in mind that after first layer you're gonna have multiple polyhedron, right? And that multiple polyhedron is gonna go into the next layer. and then so on. So you need to be you need to have function to handle multiple inputs to one layer. So I see like 3 or 4 people ask me about that, right? So that's a very basic questions, okay? And then we said about step ReLU on a polyhedron. So basically we consider to apply the ReLU operations on a specific dimension, right? So here in this example, if you apply the ReLU operation on x1 only, then you're gonna have 2 polyhedron, right? So the first polyhedron is this one. Nothing changed when you apply step ReLU. No, when you apply the ReLU activation function on S1. And then the second one is another segment here. Right? So if you don't master this, just go back and the previous class to make sure that you understand the step. Okay? And then we say the ReLU operations using step ReLU. So basically the ReLU operation we need to do to be able to compute the reachable set for a single layer can be transformed to a sequence of step ReLU operations, right? And I already saw how to do it. So after a sequence of step ReLU operations, we're gonna have the final reachable set of a ReLU operation, right? And here's on a single polyhedron, we get 4 polyhedra here. Okay. Yeah, so then when you generalize these ReLU operations, so if you have a layer with n neuron, you need to perform n step ReLU operations to be able to compute the reachable set for the layer. And I haven't say anything about how to optimize the number of step ReLU operations. Okay? So basically, you can optimize or minimize the number of step ReLU operations you need to perform. If you know before you do computation, if you know that the ranges of all neurons in the polyhedron, and then you can get rid of many neurons, and then you don't need to worry about the step ReLU operation on this neuron or this dimension. Okay, that's how you optimize the ReLU operation. And then we talk about verifications of feedforward neural network. Basically, you need to specify a property for your network, right? And then the verification problem is that you need to check whether the output set after you compute reach the property P or not. So that's the verifications problem. Okay, so that's what we have learned so far, and you already learned how to code some basic algorithm for polyhedron approach. So what we're gonna cover today is that we specifically focus on verifications for feedforward neural network. So we specify a property first, and then I'm gonna talk about the breadth-first search algorithm and deep-first search algorithm, and then something called flattening a feedforward neural network. And the reason that we flatten a feedforward neural network is because it's very efficient when you do another type of deep-first search I call flattened depth-first search. So this flattened depth-first search algorithm can very quickly find counterexample or SAT result without trying to explore all the branches when you do computation, when you do verifications. And then you're gonna see it again, why the step ReLU operation is very useful here in terms of memory consumption. So I'm gonna show you the memory consumption of different algorithms like breadth-first-search, deep-first-search, and flattened deep-first-search, okay? And then I talk about how we actually implement this algorithm. So I'm gonna show in this talk how we implement breadth-first-search in parallel manner and to speed up the verifications. So in NNV, we currently support breadth-first-search, and for the deep-first-search, I'm implemented right now. Okay, and it's still under development. Basically, it's gonna be another papers like publication for that. But I'm gonna introduce you the idea of the deep-first-search and flattened deep-first-search, and then we're gonna talk how to verify feedforward neural network using NNV. So until now, we haven't used anything in NNV, right? You only use MBT2box and write your own code, okay? Just for practicing how things gonna work. And now we come up with the NNV solution, okay? So to use NNV to verify a feedforward neural network, what you need to do is that you need to construct a feedforward neural network object, and then I'm gonna show you how to do reachability for feedforward neural network using NNV, and then how to verify feedforward neural network, and then I talk about parallel computation in NNV. So basically, right now, to speed up the verification time, we just simply increase the number of cores you use in verification. So if your computer have like 4 or 8 cores, you can use all of them to speed up the computation and then verify the problem. Okay. Any questions? Okay. All right. So let's go to the first part. We verify a feedforward neural network. So first we specify a property, right? So you already implement how to compute the reachable set for feedforward neural network. Now you want to verify a property of that network. So the first step is going to be specify a property for the feedforward neural network. So what is the property here? So the property here is a set of linear constraints on the output of the network. And this can be specified as a bounded or unbounded polyhedron or union of polyhedron. Okay. And in NNV, we specifically specify a property for feedforward neural network as an unsafe region. Okay. The unsafe region is specified by a half-space object, which basically is also a polyhedron. Okay. And it's a set of linear constraints. And that's how NNV used to specify the property of a feedforward neural network. So here is an example. So you have, again, you have this small example, 2 inputs, 2 outputs, and 1 hidden layer. So the safety property that you want to verify your network with corresponding to specific input set is, for example, you want to have Y1, the first output is smaller than 2. Okay, so this is equivalent to the unsafe regions that if Y1 is larger or equal to 2, then the network is unsafe, right? So that's how we specify a property for a network. Okay. Any questions about this? Okay. So Now we come up with the first strategy to verify the property of a fit-forward neural network. I call it breadth-first search. So the core idea of breadth-first search is we compute the reachable set layer by layer. That's what you have done in the homework, okay? And then we verify the reachable sets of the last layer, again, the property, okay? So first you have the input set, and then after the layer one, you got three outputs, right? So the layer ones, after layer ones, you're gonna have 3 polyhedron, okay? And then you go on the second layers, you're gonna get, for example, 9 polyhedron, okay? And then you compute until the last layer, you're gonna have a bunch of polyhedron, like hundreds or maybe thousands. So for the real case study, you can reach to millions of polyhedron, okay? Very huge number of polyhedron in the reachable set. Because naturally, the neural network is a very complex nonlinear function, right? It's approximate a very complex and nonlinear behavior. So that's why when you have a polyhedron input set, it's gonna give you a very complex set of outputs. So that's the point. So and then after you come to the last layer, you're gonna verify if all the outputs of the last layer intersect with the property P or not. So if there exists one output set that's reached the property P, then you say the network satisfies the property P. Okay, you only need one. Okay, so if the property P is unsafe regions, then in thousands of polyhedron in output sets, only one output intersect with the unsafe regions. You say, okay, the network is unsafe. Okay, so that's how the breadth-first search work. And now we come up with the deep-first search algorithm. So for deep-first search algorithm, it's a little bit different than the breadth-first search. So it compute the reachable set on a specific branch, and it's verify the reachable sets on that specific branch only. And it's gonna stop search when a property is satisfied. So basically, you don't need to compute all the reachable set of all layers. Okay. So here, let's go back. So you need to compute the reachable set of all layers, right? Layer by layer. And in this deep-first search, you don't need to do that. Okay, let's go. So here you have first is the input set. And then after first layer, you have 3 outputs, right? And for these 3 outputs, you only pick one to go deeper. So you pick one input in 3 outputs of the first layers, and then you go to compute the reachable set of the next layer, plus the second layer with that input set only. You don't need to compute for all input sets to the layer 2, sorry. And then you did it again. For the layer 2, you have a bunch of input set, you just pick one, okay? You go deeper. And to the last layer, you have, for example, here you have 2 polyhedron. And then you verify this. You verify these 2 polyhedron, okay? So if it's satisfy the property, then you just stop, right? You don't need to worry about the other branches, sorry. So you just stop here. But if it's unsat, what you need to do, you need to explore the rest of other branches, right? So what you need to do, you pick one polyhedron of the last layer you compute. And if it's not intersect with the property P, or it's unsat property P, right? Then you go to a next polyhedron, okay? And then if this polyhedron also does not reach the property P, what you gonna do? You're gonna go back one level, okay? So you're gonna go back to this. Do you see my mouse? Hello?
Yes.
Can you see the mouse?
Yes, we can see the mouse.
Okay, so great. So you go back to this output set of the layer 2, okay? You go back here. And then you go deeper to search or to do the reachable set again, to compute the reachable set again. Okay? So you go again, you compute the reachable set, and then you check when it comes to the last layer, you check if it's unsat or not. If it's unsat, then you go back to another output set of layer 2, and then you go back to up to one more level, okay? And then, okay. So any questions here? Is that complex?
No, it's okay.
It's okay? Okay. Do you think you can implement it quickly? You know the idea. Can you implement it? Okay. Let's talk about the implementation later. Okay. Okay, so that's the deep-first search. Now let's take comparisons between deep-first search and breadth-first search. Okay. So here you have two algorithms here. The left one is the deep-first search, and the right one is the breadth-first search. Do you have any comment about these two algorithms? So what is the difference between them, and what is the benefits of doing deep-first search?
So when we do depth first search, so do we get the property P that we want every time, like in the output?
Can you say again?
So when we are doing depth first search, so we are not getting like all the dimensions in the output, right? So are we like getting the property P that we want to check like every time? Can we do that?
I don't quite understand your question. So if you do deep-first search, you go deeper and deeper until the last layer, okay? And when you come to the last layer, you produce some polyhedron, right? And then you verify the property. And then if it does not satisfy the property P, you come back to a previous book set and do it again.
Okay.
You understand what I mean?
Yeah.
Okay. So what is the difference if we implement deep-first search here? What is the benefit?
The first search must work like faster because we're not supposed to calculate all the tree every time. Only if the output which satisfies the property P is like the very last node of the last layer, only then we will be calculating the whole tree. Otherwise, we'll stop earlier, which reduces the computational cost, the overall one.
Okay, so that's mean performance, right? The deep-first search is have better performance than the breadth-first search in general. So in general, the deep-first search is have much more, so it is much more faster than the breadth-first search when the property is satisfied. Okay, if the property P is satisfied, then the deep-first search does not need to explore all the branches, right? However, when the property P is unsatisfied, then it's gonna go all branches to prove that the property P is unsatisfied. And in that case, the deep-first search and the breadth-first search is the same, right? So that means when you verify a property P, if the property P is satisfiable, then using deep-first search, you very quickly to prove that. However, when it's unsatisfied, then the deep-first search and breadth-first search performance are the same here, right? Because you need to explore all the branches to prove that the system is safe or like something like that.
So what about when there are multiple properties?
So it's the same, right? If you have multiple properties, so you go this way, then using deep-first search, you're gonna use each reachable set at the last output layer as the last layer to verify for each property. Okay, and then if all the property are unsat, you go back and do it again. If the property there are at least one property that you are satisfied, then you're done. You stop searching. Okay, so the first benefit is that the performance. Any other benefit here? Do you think?
It seems like unless you've got a very unusual network architecture, it should reduce the maximum memory usage at any given time.
Right. So that's a very good point, okay? So when you do breadth-first search, you require a huge number of memory. And in practice, so you might end up have like your computer is gonna be crashed when they do computation because they don't have enough memory. Okay, I'm gonna show you what is the memory complexity when you do a different algorithm. Okay, so I think that's the two main benefits of deep-first search compared with breadth-first search. Let's see.
So
Memory.
under what case would you use breadth-first search?
So basically, we prefer to use deep-first search. So the breadth-first search is a very simple way to do verification, like very just do layer by layer and then check the last layer. But in practice, what we should do should be deep-first search.
Is it partly because the structure of the search tree, that this is a perfect balance tree, right? So that makes breadth-first search not really have any benefits. But if the structure is not a perfectly balanced tree, then you might want to use it. That there might be cases when you want to use breadth-first search.
What do you mean by balance?
So it's balanced here. The depth from the root to every one of the leaf is the same.
Yes, yes. You're gonna have the same, right?
Right. No, I'm saying if you don't have this perfectly balanced structure, then there might be cases when you want to use breadth first search.
So, but when you have a neural network, you have a set of layers.
Right. Yeah.
Right. From the top to the bottom.
That's what I mean. Because you have a neural network, therefore you have this perfectly balanced structure, and because of that, you always want to use depth first search.
Yes. So yeah, I agree. So in the other case, might be breadth first search is better, but in this like neural network verification, then deep first search is better. Okay, so the memory efficient, and then prove SAT quickly, right? So that's two main benefits of deep first search compared with the breadth first search. Okay, so let's move to another interesting idea. So I implement this idea already, but haven't published it yet. Okay, so it have in NLP. So flattening of a P4 neural network. So what do you mean by flattening? So this flattening technique is very useful for deep first search verification algorithm. I'm gonna show you why. Okay. So now you have, let's consider a P4 neural network like this. So you want to compute the reachable set of this network, okay? No, you want to verify a safety property. So when you want to verify a safety property or something like that, you need to have a reachability analysis, and you need to do reachability analysis, right? And then, so you want to compute the reachable set of the last layer, okay? So now you can transform this network into a sequence of operations, okay? That means you flatten the network, okay? So here you have an input set, you're gonna have input set here, right? And then the first operation you need to do when you compute the reachable set of the hidden layer is that the affine mapping operation, right? So you transform this to an affine mapping operations. And then after these affine mapping operations, what you need to do? You need to apply the step value operation, right, on the first neuron, okay? And then, again, come to the second neuron, you got a step value operation at the second neuron, right? And then you got a step value operations for the third neuron of the hidden layer. And now, what you're gonna do next? What is the next operation you need to do?
Another affine mapping, and then two ReLUs.
Okay, great. That's affine mapping, right? And then the step value operations on the first neuron, and the step value operation for the second neuron. And then you get the reachable set you want to verify, right? So you can see that from a complex architecture, neural network architecture like this, you can flatten the network into a sequence of operations when you do computation, right? So that means this neural network, when you want to do reachability analysis or verification, is actually equipped with a sequence of operations like this, right? So if you give me a neural network, and then I just transform or flatten this neural network into a set of operations, okay? And for these operations, what is the input of this operation? So the input to the affine mapping operation is gonna be what? The input set. And what? What else?
Weights and biases.
The weight matters.
Yes, that's correct, right? And then the step ReLU. So what is the input to the step ReLU? What is the input to that?
The reachability sets of the first layer, one of the polyhedrons for the first operation.
Okay, and then the direction, which is the you're correct. So you get the first, you get the polyhedron after the affine mapping operation, and then you perform the step ReLU on the first dimension, right? And yeah, so the same things happen for another operations. So from this flattening technique, do you have anything in mind? How it's gonna be, how it's gonna benefit the deep-first search?
We get rid of the ReLU operations, additional ReLU operations. As we go deeper, only one operation per branch remains, right?
Yeah, that's great. Yeah, that's correct. So that means now we don't have layer here, right? We don't care layer, okay? Instead of, so come back again. Here, in the deep-first search, you also care about the layer. And at each layer, you're gonna have several polyhedra, okay? And now I don't care about layer anymore. What I care is about the operation, okay? So we have no layer here. And a feed-forward neural network is a sequence of operations, okay? Now, let's see how we can do deep-first search with flattened feed-forward neural network. I call flattened deep-first search. So we can transform a feed-forward neural network into a binary tree, okay? So now you have an input set. And then after the first affine mapping, what do you have? How many outputs you have? The affine mapping operations. So you only have single outputs after the affine mapping operation, right? Single input, single output, right? And then you apply the step ReLU operations on the first dimension. What do you have? You have two new polyhedra, right? And then you just worry about the first polyhedra. You go deeper. You just worry about the first polyhedra, right? So you apply the step ReLU operations on the first polyhedron, and then you get two new polyhedra here, right? And you do it again. Now you come to the affine mapping. So for the affine mapping, you just get the first polyhedron, and then do affine mapping. You got a single polyhedron here, right? And then again, you apply step value operations on the first dimension and second dimension. And then you come to the last operations, right? So that's how you go. You always go with the first polyhedron in the reachable set you compute in whatever operations you're executing, right? So if you have affine mapping, you got a single polyhedron, and then you go ahead to do with that. If you have a step value, you're gonna have 2 polyhedron produced, and then you go with the first polyhedron you have. So you go deeper and deeper, okay? And then when you come to the last operations, and what you need to do, you verify, right? You verify this, and then come back to the next polyhedron, and then you verify, and then you come back 1 operations, and then do it again, okay? And then you come back to another operations, like gradual operations, and then you go. So that's how you do verification using flattened default neural networks or using flattened Depth-First-Search. Any questions? No questions? Is that complex? So, okay, so now just stay here, think a little bit about what is different between Depth-First-Search and flattened Depth-First-Search. So let's compare the memory consumption of different algorithms, okay? So let's consider Depth-First-Search first. So what is the worst case? In the worst case scenario, how many neurons, how many polyhedron you got after the first layer? How many? If n1 is the number of polyhedron of the first layer, then how many polyhedron in the reachable set you're gonna get after the first layer? No answer?
Mr. Tan, could you repeat the question, please? Excuse me.
So if you have if the first layers have n1 number of neurons, n1 neurons, then how many polyhedron you're gonna get after the first layer in the Depth-First-Search algorithm?
Three multiplied by n1?
No. Here I just plot 3, right?
Oh, not 3, I mean.
That's right. 2 power n1. That's the maximum number of polyhedron after the first layer. Okay. And now come to the second layer. Because you only handle 1 single neuron you just pick 1 single neuron of the first layer to perform the reachability and to compute the reachable set for the next layer, right? And then the number of the maximum number of polyhedron in the second layer is going to be n power n2. That's right. That's correct.
Yep.
Okay. You need to interact with me to make sure that you understand it. Okay. If you don't understand it, just ask me questions. Okay. Okay, and then when you come to the last layer, this is what you get, right? 2 power n. Okay. So the total reachable set you get for verification is how many? This one, right? So when you use single cores for computation, okay, this is the number of polyhedron you need to store when you do computation, when you do verification. I mean here, the deep first search for a single core or single thread. And you need to have to, you need to store this number of polyhedron when you do computation, right? And now let's consider the breadth-first search. So after first layer, you got the same, right? 2 power n 1. What is the next layer? What is the number of polyhedron for the second layer?
Same thing for each layer.
N into to the power n.
Yeah, based on the number of neurons in that layer.
What? Can you say again? Any answer? Oh, hell. Okay, what is the answer?
To power n2 multiplied by number of neurons.
Yeah, each neuron create another exponential number of polyhedrons, I guess.
Yeah.
So you mean n1 times 2 power n2?
Yeah, something like that. Yeah.
Can you write down in the chat? Thus everyone can see it.
No, it's actually going to be 2 power n1 multiplied by 2 power n2. Because in the previous layer, we have 2 power n2 neurons.
Yes, that's the correct answer, right? Here. Okay, so when you come to the last layer, what you can imagine, how many neurons you have? A lot. No, how many polyhedron you have? A lot, right? And so for single core, single thread again, this is the number of the reachable set you need to store when you verify the profit. So you can see the breadth-first search require much more memory than the deep-first search. Okay. Any questions here? No questions? Okay, good. So now let's consider the deep-first search and the flattened deep-first search. Okay. So when you have flattened deep-first search, after the first operations, you're gonna have 1 only because it's affine mapping. After the second operations, which is the step value operation on the first neuron, on the first dimension, is gonna give you 2, right? And then another 2, and then another 2, and 1, and 2, and 2. So in total, this is the number of polyhedron you need to store when you verify the property. So it's really nice, right? In terms of, you can see, deep versus the number of polyhedron you need to store still exponentially, right? Even it's better than deep search. However, in the flattened deep search, the memories increase linearly with the total number of neurons in the network. Right? That's amazing, right? Here, you can see. So for deep first search or breadth first search, you're gonna have the memory complexity is exponentially corresponding to the number of neurons in the network. Okay. And in the flattened deep-first search, then the memory is very efficient. Okay. So the memory you have is linearly increased with the total number of neurons of the network. Okay. Any questions so far?
Can you go back to the previous slide 16? So when you are, say, at the third layer for BFS, where you have n+1 times 2 to the n2, then you say that the memory consumption at that point is 1 plus 2 to the n+1 plus 2 to the n+1 plus n+2, right?
So basically, in terms of store, that's how memory is only stored 2 power n1 time and 2 power n2. So this complexity is the total polyhedron you need to store for the computation. It's not like it's not exactly how the memory consuming the computation. Basically, at each layer, you only need to store this one, right? So for each layer, you only need to store this one. You don't need to worry about the previous layer, right?
Right. So I think that's what I'm getting at, is that once you get to the third layer, then you don't need to remember all the things that you stored before.
Yes, just for debugging. So just for debugging, you can store.
And but if you don't care about debugging, then the total time is just the last one.
Yes, that's correct. Yeah, I agree.
Okay.
Yeah. So here is that if I want to store all the reachable set, then this is the complexity, right? But to be yeah. So in practice, we don't need to worry about the previous layers. So there one case that you need to worry about the previous layer is that if something happens, so if you are computing, if you are verifying the network and then something just crash, and then when you have these reachable sets stored, then you can resume the computation right after, so right to the place where the crash is, where crash happens. So that's the one benefit of storing all the reachable set you need when you do computation. But yeah, you're right. You don't need to worry too much about the previous layers reachable sets, right? And then if you do that, then the total the memory's complexity is gonna be this term only. Oh, sorry, this term, the last one only, right? Did that answer the question?
Yes.
Okay. Okay. So, and here, so the same. So if you don't want to care about the total of reachable set you store when you do computation, then at any time you have at most 2 reachable set you need to store, right? Here, that's the complexity of storing, and then yeah, just forget about the previous operations. Okay. So now let I take a conclusion for this. For memory consumption, you can see that breadth first search is consume more memory than deep first search, and deep first search consume much more memory than flattened diffusion, right? And this is the complexity when you want to store all the reachable set when you do computation. Okay, I should take a note here, right, to explain it more accurate. So now we come with the implementation. Okay, so in NMV right now we have a very simple breadth-first search implementation. So the idea is that you're gonna compute the reachable set layer by layer, and then when you come to the last layer, you check the intercept of the reachable set with the property P. Okay? So that's how the breadth-first search work. Okay, so this is the video I'm gonna show you how to do it. So in this video, I'm gonna show you how to verify a safety property of a FFNN neural network using breadth-first search. So first we generate an input set, polyhedron input set. Here I generate a box, a 2D box, and then we randomly generate our FFNN neural network, weight matrices, and bias vectors. So here we have the neural network have 2 inputs, one hidden layer with 3 neurons and 2 outputs. Okay, and then the safety property here is that we want to have the property defined by a box, another box here, like y1 is between 0 and 1, y2 is between 1 and 2. Okay, so we construct property P here. So to verify the network, we write a verify ReLU FFNN neural network breadth-first search function here. So the input to this function is the weight, bias, input set, and the property P. Okay. So what this verify function does? So the verify function is gonna do first. It's gonna compute the reachable set of the network using breadth-first search, which is layer by layer computations. So after it compute the reachable set of the network, it's gonna check whether or not each element in the reachable set or each part of the reachable set intersect with the the property or not. So if it intersect with the property, then we say it satisfies the property. So satisfied is equal to 1 here. And then we loop over all the reachable sets in the reachable set we compute. Okay, so the rich breadth-first search function basically that's what you have done in the practice. So basically, it's gonna call the ReLU layer rich with multiple input functions. That means after the first layers, you have multiple outputs, right? And that's outputs gonna go to the next layer. And then you need to handle multiple inputs for the next layer. So that's why we need to have the ReLU layer rich multiple inputs function here. And this basically just call ReLU layer rich for a single input function and then compute layer by layers. So that's how it works. Okay, let's see the result. Okay, so here the red one is the property P, okay? And the yellow one is the reachable set of the network. So in this case, we can see that the reachable set did not reach the property P. So you can check. And now if we run another one, and here you can see the reachable set kind of reach the property P. Let's check that. Oh, that's still 0. That means it's not satisfied. Let's get another one. So in this one, you can see that the reachable set reached the property P. So let's check that equal to 1, right? So that's how we write a verify function for FFNN neural networks using breadth-first search algorithm. Thank you. Okay, so here's the questions. So that means that we have found the reachable set intersects with the safety set. Yes. So so when you have safety sets described, don't say safety set, okay? It's just a property P. And the property P can define the unsafe regions in general. So in NV, we call unsafe regions. So when the network or the reachable set reaches the unsafe regions, then the network is unsafe. Otherwise, it's safe, right? Does answer your question, Elena? Yeah. So you just call it property P in general, and then if the reachable set reaches the property P, then it's satisfied. Otherwise, satisfied, something like that. And then you can specify the property P as unsafe regions. I'm gonna show you later in NNB. Okay. So I think we just have a little bit time. So let's consider a very interesting idea how to implement Depth-First-Search. Just idea, okay? Maybe you have a better idea. So in this video, I'm gonna show you how to verify a safety property of a. Okay, so how we implement Depth-First-Search? So so when you want to implement Depth-First-Search, the first question we need to answer is that how we're gonna store the reachable set over layers, right? You need to somehow store the reachable set over layers and then compute the reachable set until the last layer and then verify. Okay. So the idea for implementation. So this is my implementation idea. Okay. You might end up with another idea for implementation, but the idea of Depth-First-Search implementation should be very different from Breadth-First-Search implementation. And I'm gonna explain you why we need to do that. So in Breadth-First-Search, so you have layer and reach, right? You can be reachable set layer by layer, right? And layer is the center of the reachability, right? So when you come to the layer, then you handle multiple invokes to that layer, and then you can build the reachable set at that layer. However, in the Depth-First-Search algorithm, what you care is you care about, you just pick one output set of a layer and then perform the reachability of that output set for the next layer, right? And then you're gonna shift the center of the computations from the layer to the reachable set itself. It's not the layer anymore. So that means you need to have, so you need to support the reachability methods for the reachable set itself. And the input to that reach method is gonna be the layer, the next layer, right? So this is how we can implement the Depth-First-Search in an efficient way, okay? So any idea for other implementation we might have for this? No? So the Depth-First-Search implementation, in my opinion, we should shift from the layers is the center of the reachability to the input set is the center. So that's the core idea here, right? So you're gonna store input set in the stack, and then when you get out of that stack, and then you just compute the reachable set when you have the next layer in books, ascending book. Any questions here? Any suggestion? No question? No suggestion? Okay. Okay. All right. So that's the deep-first search implementation, in my opinion. Okay. Maybe you end up with another better idea than mine, and then you are very welcome to try to implement the deep-first search algorithm, and then you can compare the performance. Okay. Now let's come to the last slide. So how we're going to implement the flattened Depth-First-Search. So do you think how it's going to be different from the Depth-First-Search? So when you come to flattened Depth-First-Search. So the core question is how you store the reachable set over operations. Okay, come repeated. The main question is how you store the reachable set over layers. Okay, and now when you have flattened Depth-First-Search, the core question is going to be how you store the reachable set over operations. Okay, and then the idea here is that you also use in books, use the reachable set is the center of the computation. That means you need to shift the reachability matters to the set, okay? And then for the Depth-First-Search, the input to that reachable to that reachability matter is going to be the layer, the next layer, right? However, in the flattened Depth-First-Search, the input to the reachability matter is going to be the next operation. Right? It's very simple, right? So they are basically they have the same idea, just they have different input to the reachability matters. Okay? Okay, so I think that's all for today. Hopefully you enjoy this class. So I discussed several ideas about how to do verifications for feedforward neural network efficiently in terms of timing performance as well as memory consumption. And then I discussed how to implement Depth-First-Search and flattened Depth-First-Search algorithm. I haven't talked about how we actually do this in parallel in a parallel way, right? So how you in this class we're gonna explore how we use parallel computations to speed up our verification. Okay, that's a very interesting idea when you come up when you come with the Depth-First-Search algorithm. So how to do parallel computations for Depth-First-Search algorithm is also a very interesting problem, and then we're going to discuss in the next class. Okay, so any questions for today? All right, so yeah, hope you enjoy the class, and see you on Thursday. Thank you.
Thank you, Dr. Chen.
Yeah.
Thank you.
Thank you. Bye-bye.
Do you have office hour now?
Yes, yes.
Yeah. Okay, I want to ask some